Okay, so this here is there is this metal group, right? And it has 3 hydrogen there, and we put its HA, hydrogen A, or simply put A, and hydrogen B here, right? And you can see this hydrogen here and this hydrogen here are what? They're equivalent, right? They are equivalent. They are symmetrical. You see that this structure. So this is hydrogen A. This is also hydrogen A. They are chemically equivalent. Therefore, they are chemical shift equivalent. So you can only see one signal from this. Surely, these 3 hydrogen are. I mean, this is. It has 3 hydrogen here. So hydrogen A, right? Surely there are 3 of them. And these hydrogen, 3 hydrogen, and these 3 hydrogen are equivalent. Remember? They're equivalent. They are chemically equivalent. Therefore, you can only see one signal. Similarly, for hydrogen B, there are 2 hydrogen here and there are 2 hydrogen here. These 2 hydrogen are also equivalent. Right? Also equivalent. That's the reason you can only see 2 signals. But which one is A, which one is B? Then we take a look at this. So, let me see. Okay, and there are 2 hydrogen B. So, you see, this one, they are both 1 bond away from this carbon-carbon double bond. But which one will have higher electron density? This one has higher electron density, or this? Let's just compare these 2. You see, there's hydrogen B, and there's hydrogen B. So you can see that both of them 1, 2, 3 bond away. 1, 2, 3 bond away from oxygen. But which hydrogen has higher density? So normally, this has lower electron density, CH2. We go check the table. So actually, I don't recommend you do this assignment using this table. I do not recommend. You know, yeah. But now you do it. You know, you follow this, but then you need to find the trend, because we will take all this MCAD or GRE, such value will not be provided. And there's no way for us to memorize all of this. You only need to memorize a few specific cases, like a double-double bond, like the benzene group, something like that. For all the others, we can get a trend. So it's better for us to find a trend. You see that table 9.1. We need to get a trend. So these usually have higher chemical shift, right? You see that have higher chemical shift. If you see this higher chemical shift. Why? Because it's lower electron density. Right? Because it has 3 hydrogen, it has 2 hydrogen. The electron density is lower. The electron density is lower, right? there are more electrons. When there are more electrons, the electron density is higher. Right? You can just imagine, in one area you have 2 hydrogen, in the other area you have 3. Then there are more electrons. When there are more electrons, more electron density, or we put higher electron density, then higher electron density will generate more magnetic field, right? To counter the external magnetic field generated by the equipment. Therefore, the net magnetic field should be lower, right? The net magnetic field is lower. When the net magnetic field is lower, the energy difference between these two magnetic states is smaller, right? So, yeah, you see, yes?
So will the HA peak be smaller or bigger than the HB peak on the NMR?
Oh, it depends on how many of them. You see here, HA has 3, right? You see, for HA there are 6 of them. For hydrogen B there are 4 of them. That's the reason it match. So the left signal should be B, should come from B, right? From hydrogen B. Yeah, you see, they agree with each other. We analyze from the chemical shift and from the number of hydrogen. You see, so the signal on the left has higher chemical shift, right? And then why? Because it has lower electron density. Why? Because it has less hydrogen there, right? In the same area, if there are 2 of them, there are 3 of them, this has less electron, has lower electron density. When it has lower electron density, it's called what field? It's called low field. Low field. Yes?
So in a situation like this where you said you had 6 HAs.
Oh, 6 HA, yeah.
Yeah, and then 4 HBs. How do you weigh which one ends up having more of a higher density? Because, or like ends up having more of a chemical shift? Because like say like there's only 1 HB and still 6 HAs, would that mean that the HA would have a higher chemical shift?
It applies to this case. There's other factors. Here, for example, this hydrogen A and hydrogen B are both 3 bonds away from this oxygen, right? There are some other factors. We cannot just use one. Yeah, there are other factors. What I mean that, when you take exam, normally these values, this table won't be provided to you, and there's no need. You don't need to memorize all of them. You just need to memorize a few unique cases. For all the others, we can use this chemical shift and the splitting, chemical shift and the splitting. We can use all this to, as we can see, we can solve all these problems. We don't have to refer to the table. So that's the reason I keep repeating this concept, higher electron density. High electron density is called high field. High field will generate, the electrons will generate higher magnetic field to counter the external magnetic field, because they are just opposite to each other, right? Remember, they are opposite to each other. Then the net magnetic field is the external magnetic field minus the magnetic field generated by these electrons. So you see, B has higher chemical shift, and there are only 4 hydrogen B. So that's the reason. There are 4 hydrogen B and 6 hydrogen A. That's the reason the peak is lower, is shorter than the peak from hydrogen A. So. Yeah, if we apply these rules again and again and again, you only need to remember a few, unique cases. You don't have to memorize all of these. There's no way. No one can remember all of this. So let's take a look at the page 36. So I got A, B, C, no, sorry, there's no A, B, C, D, right? And then, yes?
Sorry, no, you're good.
Oh, okay. So without looking at the table, we have figured out. You don't need to look at the table. Okay. You don't need to look at the table. You see, there's hydrogen here, there's hydrogen here. We know oxygen has a very strong capability to attract electrons, right? So the closer the hydrogen to oxygen, the more electrons will be not taken, will not be. Let's just use this word, taken, right? But we know we need to keep in mind is covalent bond. The electrons cannot be completely given away, just partially. Okay. So the closer the hydrogen to oxygen, the closer the hydrogen to oxygen, the more electrons will be given away to oxygen, right? When the more electrons are given away to oxygen, therefore the electron density will be lower. When the electron density is lower, then less magnetic field will be generated from these orbiting electrons. When less magnetic field will be generated by the rotating electrons, the net magnetic field equals the external magnetic field minus the magnetic field generated by these electrons will be larger, right? So the net magnetic field will be larger. And when the net magnetic field is larger, the energy difference between these two magnetic states will be bigger. And then it needs more energy. When it needs more energy, the frequency will be larger, and then the chemical sheet will be larger.
So it's a bigger peak if it's like closer to oxygen,
Yeah.
basically?
Yeah.
Okay.
Yeah. The bigger the chemical sheet.
Yeah.
Yeah. So you can see that CD are equally close, right, to oxygen. But then we go back to this. There are only two hydrogen here. Two hydrogen here. There are three hydrogen here, right? So then the hydrogen here should have even lower density than the hydrogen here because it has CH2, not CH3. So C should be the most left, followed by D, right? And then followed by B, followed by A. You don't need to refer to this table, right? C and D, the hydrogen here are both 1, 2, 3 bonds away from oxygen, right? Then C and D should be the lowest, but C, the hydrogen C here only has 2 of them, and there are 3 of them. Then let's refer to that rule. Should be C, D, B, A. You see that? We don't need, it's impossible for you to remember all of this. And we don't need. We only need to memorize a few.
So is this how you want us to label the labs? Like, so these peaks, it's going to be like, the tallest peak is going to be C for this one, and that's how we're labeling it?
Yeah, you just label the peak, for C, D, B, A.
Yeah, okay.
Yeah, just below, yeah, you just label this peak, C, D, B, A. Yeah. Yes?
I'm sorry, I'm so confused. So does that just mean like in the order that they appear? So like
Yeah.
this would be C, this would be
Yeah.
Okay.
Or you can put along this line, to be, either way. You can put on top of the peak, or you can put at the bottom. Either way,
Thank you.
no problem.
How come this one has
7.
So like, chemically, it's like,
So we get A, B, C, D, E, right? A, B, C, D, E. And then we discuss what? We discuss the decoupling effect, right? Decoupling effect due to what? Fast chemical change. Because this hydrogen can be exchanged between molecules, then it has a very different mechanism. So even though this hydrogen is directly connected to this oxygen, but the mechanism is different. But we need to keep in mind, remember, for the rapid chemical, when there's a rapid chemical exchange, this hydrogen cannot decouple with the labor, right? They cannot decouple. They cannot couple each other. They cannot couple each other. Remember, we have the slide. We have a few slides. So the hydrogen here cannot couple with the hydrogen here. So that's the reason. For all hydrogen directly connect to oxygen, it has only one. The signal has only one peak, because there is no coupling. There's no coupling. So then you can see that from here, there's only one signal that has only one peak, which is the middle one, right? The sharp one. The middle one has only, if we count from left to right, the second left has only one peak. The signal has only one peak. So that one should be B. Should be B. And then C should be, you see, C, for all the other hydrogen, C is what? The closest, right, to oxygen. So the leftmost should be C, right? And the second one should be B. Why? Because there's no coupling. The hydrogen from OH group, from NH group, from carboxylic acid group can only have the signal can only have one peak. So there's a hydrogen here, 1, 2, 3, 3 bonds away, right? But even though the distance is 3 bonds, but there's no coupling effect, right? Because this hydrogen gets involved in a rapid chemical exchange process because it dissociates, there is a rapid exchange process. So NMRs like take photo. So if I take a photo of you and you move around very quick, then we cannot take a good picture. And it's blurred, okay. At the best, it's blurred. Same thing here. So that's the reason this hydrogen connect to oxygen can only have the signal can only have one peak, single peak. No splitting. So, and this hydrogen is closest to oxygen, right, among all the other hydrogen. So C should have the largest chemical shift, followed by B. B is because it is single peak. And then we can compare. Then we can compare A and D. A and D, the hydrogen from here and the hydrogen from here are have the same distance, right, to oxygen. However, this is CH3 again. This is CH2 again. Then this should be D, A, E. Right? You don't need to use the table. We have these principles in our mind. When we have this principle, all these principles about what? About the electron density. Why CH2? Why the hydrogen in CH2 has higher chemical shift than hydrogen in CH3? Because it has lower electron density. And then the fourth page is the is carbon-13 NMR. Yes?
So where you put D, is that supposed to be there? Because there's not another hydrogen there.
Oh, this one is, I'm sorry, this is a carbon 13 NMR. And you see the value are very big, 100, 200, 200 something. It's carbon 13.
Mm-hmm. Okay.
It's carbon 13 NMR. Yeah, we should put, we should let, this carbon 13.
Yeah.
You see, for proton NMR, the highest value is 15, or 10 or 15. I don't remember that. I think 15. Yeah. The highest value is 15, and here is 200. If it is above, 20, then it's carbon 13 NMR. Yeah. You see, again, this carbon is directly connected to oxygen. Then it must have the lowest electron density. When it has the lowest electron density, it must have the highest chemical shift. So D is the most left. And then for these things, we need to remember, because of the limited time, we don't discuss this, but you just need to have this idea that the chemical shift for carbon for carbon-carbon double bond is in this range. Is in this range. And you see, if you check the textbook, let me see. Oh yeah, carbon 13 is here. Oh, is figure 9.29. You see carbon-carbon double bond, and this benzene group, the carbon-carbon bond is around 110 to 150, for carbon-carbon double bond. For the carbon in the carbon-carbon double bond, the chemical shift is 110 to 150 ppm. You just need to memorize such kind of thing. Okay, this is very unique. And because of limited time, we don't want to go through the mechanism. You just memorize this. You don't memorize the whole thing. You just memorize a few unique things. For all the other things, you can apply these principles again and again. So, and now A and B, this A and B and the carbon A, carbon B are from the same double bond, right? So which one have lower chemical density? Yes?
Would it be B?
B, yeah, because B is close to oxygen. Then B should have higher. It should be BA. B should have higher chemical shift, BA. And then there's C and the E. So which one? So C and E, yeah, so yeah, we need to keep in mind this double bond lacks electrons. Therefore, the carbon here, if we compare these two, this carbon should have less electrons. Why? Because this is connected to what? Carbon H, and this is connected to carbon H3. It has more electrons. We just compared the electrons, right? Because this CH, this CH3, CH3 have more electrons. Therefore, E, compared to C, E should have more electrons, and the C should have less. Then should be C, and then E, and then F. Right? We just compare the electron density. Let's keep comparing the electron density. Well, any questions? And then, yeah, I will leave you to work on the remaining, and we can discuss. If you have any questions, we can discuss. Okay. And then you can submit this 1 week. We meet. I mean, next Friday. So, yeah, you can work on this, and we can discuss. If you have any questions? It's all about comparing the electron density, electron density, electron density. It's because it's all about electron density.